I don't know about you, but finding faults can sometimes take me hours. But I just tested a new way to find them much faster and easier, which already helped me several times. In this video, I will show you exactly how this new method works and how you can use it for your tinkering. All you need is this. And if you ask yourself, what the hell is that? Just keep watching. It might just change how you find faults yourself forever. Let's do a quick dive. A thermal imaging camera shows you the heat that objects give off, instead of the light you normally see with your eyes. It picks up invisible infrared radiation and shows them as different colors to let you know which areas are warmer or cooler. Let me show it to you with this hot coffee and these ice cubes. As you can see, the coffee has more amber colors and this means it is quite warm. The ice cubes instead are cold, which we see with the darker bluish colors. When I put the ice cubes in the coffee, you can see the difference even better. Have a look how this looks like. But what does this experiment have to do with our fault finding? Nothing! That's why I grab a new coffee and see you at my workspace. Coffee. Nice. We have today two cases in total. In the first case, we are taking a look at an old MacBook board that apparently has a short circuit. Or does it? In the second case, I have got another board where the 3.3 power rail is acting up. In both cases, we are turning to the thermal camera. Let's see what happens. First of all, we need a thermal imaging camera. Luckily, I have an image camera at my hands. Kwait sent it to me for this video to show you guys what is possible with a thermal imaging camera. And by the way, Kwaits have no influence on the stuff I'm saying about this camera, I promise. No idea why companies have such funny names for their products, but yeah. We have a nice carrying box. I mean, come on, that's often an accessory that costs alone 30 bucks or more. And of course, the camera itself. So it doesn't feel cheap at all. But of course, I mean, we're not paying 700 bucks for a thermal camera. It's a quite good price tag, and Kwait also got me an exclusive discount, and I will put it all down in the description. So, but enough talking. So this one is not especially for electronics, but one after another. So we'll start with the MacBook. The MacBook, by the way, is this old thing over here. As you can see, it's really beat up, and that's why I just use it for this experiment. But it does have the glowing Apple logo. I would love to see this again on the newer models. The board is connected to my lab power supply, right where the MacBook's normal power would go. And if you ask how do I know which voltage, etc., I just Google it, so nothing special. So okay, so we power the board, yeah? Now let's have a look. Here's the power supply. So as you can see, this here goes to this, leads directly into this lab power supply. So, and I entered 16 volts, I think it's 16 and a half normally. And what is important when we use a power supply for this technique, it's power injection, so to say. We will start with a low current. So I can limit my output with this dial here, for example, to 300 milliamps. So this lab power supply, or everything we connect to it, will never exceed this 300 milliamps power limit. That's very important. It helps us finding fault without doing more harm as good. So as you can see, here is no red LED flashing. That means it's actually not turned on. I can do that now with the output button. What you do see, it is flickering around. I'm not sure if it's visible on camera, but it's always ticking between 15 volts, 16 volts, and the limits here. And you see CC is blinking. So this means there is actually a problem and it's pulling the complete 300 milliamps. So this back and forth is not right. So this tells us we do have a short circuit. Let's disable it again and measure if we can find a short. So what I will do now is easy. I turned off the lab power supply, and now we will do just measuring the ohms between, the input power. And as you can see, that's not close to a short circuit, huh? I mean, we're talking about nearly 2 kilo ohms. So that is strange. And the reason for this is the complete motherboard has their own protections on board. That means the board detects, in some cases of course, that there is a problem and shut the areas down with, for example, MOSFETs, which more or less means turning things on and off. Let's grab our thermal imaging camera, turn it on, take a zip. It always takes sometimes to boot up the system. And you hear clicking noises. That means that the sensor is calibrating. It's doing this periodically. That's normal. So now we open it up. So we see here in this example 3 point. The reddish one is the hottest point in the image. The white one is just the point where, the center point where we exactly want to have a look on something. And the green one is the coldest spot. And we even see where I put the coffee a moment ago, right next to it. I always like stuff like this. I think it's a bit magical. So, okay. So when we now have a look at the thermal imaging camera, you see there are some spots that do appear hot, but that are just reflections. As you can see here, we do have the aluminium stuff, and heat will be reflected to the camera, and it appears hotter as it is. So as you can see, and when I'm roaming around with the camera, all the heat of my face that we can see on these metal surfaces. Okay. So, but we haven't turned it on yet. So let us turn on the power supply and scan the board. As I told you, there is nothing. We see here some heat. We have here something that's getting hotter. And we have here something that's getting hotter. And now you might see another problem. These cameras are normally not for this close operation. I mean, we're talking about, this far away, so there is no focus point for this short distance. To get around this, you can buy macro lenses. That's not just, some roundish coated glass lenses you can put over this, but you need a holder for this. And I had just found one 3D printable adapter for this one here, but it was $8. So I just thought, why not doing my own one and give it to you for free, also in the description. So you are able, if you have a 3D printer, to do it on your own. I will show it to you in a moment. So as you can see here, there is heat, so the yellow stuff around means there are hotter areas, but you see it's not clear to see what it is exactly. So now let's use our macro lens to see what I'm talking about. And this looks like this basically. So I just inserted here the macro lens. You can buy them on, I don't know, eBay, Amazon, you name it, or AliExpress, it doesn't matter. And I just press it in here, it's press fit. We do have here a notch, which aligns with this over here. And when we put it on here, we have a nice press fit. Et voila. And when we now go closer, we can exactly see what is happening here. And I like to use a spotter to pinpoint it exactly, so I just go under it and we see this here is getting quite hot. What is it? And that's some IC. So this could be potentially the problem, or just one of the protection mechanisms of the MacBook, for example, because as you might remember, the power lab supply is quickly turning on and off. So there are something on this board protection which causes this. So what else do we see? What is that? We have something here. Have a look. That's quite hot. 60 degrees C. That's always, or not always, but often a sign that something gets really hot. I mean, sometimes a voltage regulator or stuff like this could go this high, but yeah, most of the time it's not that healthy. So, and if we have now here a closer look, let's see where it is. It is exactly this dude over here. Let us grab our trusted microscope camera to see what is happening. Put it over here. And we see that I did a short circuit here with a small wire. That was exactly what we have seen under our camera. So let's have a look again with the thermal camera. Yeah, we can clearly see it under the microscope camera, under the thermal camera. And that's the beauty of this macro lens. Have a look when I detach it again. Oops. You see, yeah, it's possible to spot it, but it's much blurrier. So if we have many components in this area, it's very hard to see which is showing the heat signatures. So it's a good idea to get some of the macro lenses, so to say. So macro lens back on. And we see again 60 degrees. We identified the short circuit in this case. Let's see what happens when we remove it. Let me power off the power supply and you see immediately how it fades out. It's still warm, the area, so you also see very little heat differences. That's totally nice and great. And here is the culprit. This is a MOSFET, what you see here, and it just mimics, or the jumper cable just mimics short circuit to the MOSFET. So, okay, so we swap the MOSFET, or remove the short at least, and let's have a look again how it's behaving. And you can clearly see it's not drawing nearly as much amperage as before. So now there is nothing clicking, there is nothing changing, it's just 19 milliamps. So that looks pretty good. And as you can see, there are no more heat spots. So that looks totally normal, nothing special in here. So that was the first example. When we have an extreme heat spot, this is often be the culprit. Let's have a look at the other side. Here we have something that's getting hotter. We're talking about 33 degrees C. This means that is not very hot. That's less than our body temperature. Let's see if I found the setting for the auto off. Couldn't be that hard to find. Yeah, there it is. Auto shut off to 5 minutes. Yeah, let's do 20 minutes. I think that's a fair amount. Okay. Yeah, okay. And what is getting warm is Remember, this is again the macro lens. That's just an EC, but that's not very hard. I mean, as I told you, 32 degrees C, that's nearly nothing. So yeah, let's just out of curiosity measure again let me turn off the power supply, the input resistance, and see if it changed. We had 2 kilo ohms beforehand. What do we have now? And you see there is not really, there is not really a difference. I mean, it's still around 2 kilo ohms and it's climbing, but yeah, it's close enough, I guess. And this means you can, or you're not able to determine if there is a short on the motherboard in this example with just checking the input side. Sometimes there are just sub areas where the problem occurs, and that's where the thermal imaging camera shines and can pinpoint you to the right direction. So this was the easy part. So the hardest thing was indeed the error. Now let's have a look at the other board. To be honest, I'm not sure what it was. It looks like, yeah, some kind of hard disk drive adapter. So here we have something differently. But let's have a look what this here will give us. So we will power it again, but this time we can power it directly with this power jack over here. It's taking 12 volts. Let's power it again with our power lab supply. It's connected, nice, and we see 12 volts, 300 milliamps, and let's give power to it. And as you can see, it's pulling the complete 300 milliamps. But what you also see is the current. Let me switch it back. So it's normally 12, but to give us the limit of 300 milliamps, it has to reduce the voltage. That's just Ohm's law in this case. So when we power it on, the power drops to 5 volts to have our 300 milliamps limit. So when we reduce it to 200, you see it's slightly changing the voltage accordingly. That's clearly too much. 300. That's not right. And even that the 12 volt drops to 5 volts, that's a clear indicator that we do have a short circuit here. So let's measure again. So I turn off the lab power supply. Let's see again what we will measure. And we measure again, yeah, 2 kilo ohms. So no short or something. Okay, so that's simpler. Let's power it again. We can have a look with the microscope and let's see if we find something obvious. Yeah, it looks dirty. There's some flux. So yeah, but there is nothing visible to our eyes, yeah? So what could pinpoint us to the right direction? So the easiest way in this case is again to use our thermal imager. So let's grab it. I will remove the macro lens again for the first inspection. So that's easier to have more on the screen. And if we do have an area where we would like to have a closer look, we use the macro lens again. Okay, so we powered it and you see that there is something getting really hot. But what you also see is that this heat is spreading. So it's not just one component, as you can see, but it's shining through or whatever. It's not really clear what's happening. So let's put the macro lens on it. And we see, yeah, there is something getting hot. Let's use again here the spotcher and let's have a look what it is. And you see where I pinpointed here, I will get up to, there is nothing. So this means this side is not the thing, or it's not the side we are looking for. It must be on the other side, the bottom side of the board. So let's flip it around, and we see more components. So let's do it again, removing the macro lens, and we see there's something getting really hot. See the macro lens and getting closer to it. And we see, yes, there is something getting really hot. And this one over here is a voltage regulator. It's 62 degrees, so quite warm again, or hot. So this area, let's have a closer look. So there it is. So let's measure. Maybe I can put it more to the side that we can see the multimeter. Yeah, that's better. Okay. Let's measure voltage. One lead to ground, and let's see what we have here. The bottom side, 1 volt. Nothing. Nothing. So that's not right. We should see here, I don't know, a voltage around 5 volts, for example, powering this. And this must be a 3.3 volt regulator. We can see this with the 33C. This means a 3.3 volt regulator. But there is nothing. There is nothing at the output. There's nothing. And there are just 1 volt. So it doesn't make any sense. So there's definitely something wrong with it, isn't it? I mean, it's clearly showing us some heat. Now we would think, yeah, that's the faulty component. Let's remove it. But is it really the regulator? Let's have a closer look around it. What's always important is to have a visual inspection. So sometimes you see that there is a component defective with a crack, for example. If we would see that here is a crack, that definitely means that this component is faulty. So it could be the problem. So always think and make the right decisions, and always check if there are loose connections, like solder joints. Sometimes solder joints are just cold, so you could nudge them with your spatula or the tweezer. If you see that, that could also be the problem when you see a heat spot. So in this case here, we can't see a damage. It looks fine so far. So from visual perspective, this looks fine. This looks fine. This. But let's have a look here. So that's the output of the regulator. And what we see here, again, a little jump, sneaky jump wire I just prepared. So we do have here a shorted capacitor, but the heat is not here generated. It's generated here. So it's some kind of feedback loop, so to say. So it's not always as it seems. If it's getting hot, you would just change this one here. The problem wouldn't be fixed because this is the culprit. So always check all around. So, okay, as we now know that this capacitor is defective, let's have a look. I will disable the power lab supply for a moment and let's measure this capacitor. So not only this one is shorted, everything on the line is shorted. So that's why a thermal imaging camera can be very helpful. And we see here that's not shorted, so that's fine. So it's always a combination with the multimeter, your eyes, and your experience, of course. So if I wouldn't have prepared this error, I would, of course, try and error this if I won't see any discoloration or cracks or something similar. And then we could do it like this. For example, removing this first and see if it's still there, the short, and so on. So, but this is a very good indicator, so that's getting hot, so it must be around in the area. Well, that's often the case. So, perfect. Yeah, let's remove the faulty cap and replace it, so to say. Whoop. And yes, I still disable the power lab supply. Don't do that when you have power on the board, otherwise you will short something out. So let's clean it up. Yeah, it's not the best job in the world, but just for showing, that is definitely good enough. So, okay, we remove the short, so let's power it again, and you see exactly that it's behaving normal now. We still have the steady 12 volts, we just put it in, and you see 118 milliamp. That's not that suspicious than our limit. It's still rising, which makes sense because it is a voltage regulator and there must be something dissipating with the heat. And if we now measure with the multimeter, we see here 5 volt comes in, and here we have the 3.3 volt, and that should be ground, and this is connected together. Now that you can spot those hidden faults, don't stop there, fix them. My next video shows you practical ways to handle common repair challenges, so you can get your device running again fast. Curious? What are you waiting for? And as always, happy tinkering!